So as I have said, with volumes of solids of revolution, a chosen area is being rotated on a specified axis. So a specified axis could be any of the axes that we have in the Cartesian plane, or it could be a different line specified in the problem wherein a particular area we are to rotate on. When we rotate a particular area to this axis, we are forming what we call solids of revolution. And integral calculus is being used as a tool in determining the volume of this solid of revolution. Now, there are actually three different methods that are used in determining the volume of a particular solid. So that solid can be a simple solid like a cylinder or a washer or a disc, or it could be complicated. It could be as complicated as an irregular solid, or we call it a composite solid. So what we do, since it's irregular, it's composed of several shapes, we rotate a particular chosen area on a chosen axis of revolution and then sum up the volumes of the solids that are being formed when we rotate a particular chosen area on an axis. Okay, so for this afternoon, we'll start with this method. Actually, it's the simplest method in determining volumes of solids. Okay, so for our learning objectives, at the end of this topic, you should be able to find the volume of revolution using the disk method. The second is the volume of the solid of revolution using the washer method. And the last would be the shell method. You know what a disk is. So your 1 peso coin is a sample of a disk. Okay? A compact disk is a disk minus the hole in the center, because the hole in the center of the compact disk makes it already not a disk but a washer. But anyways, I will give you specific examples of these three solids, the disk, the washer, and the shell, before we tackle sample problems which produces these particular solids. Now, you could see here different solids. Okay? Area is only one of the applications of integration. So we can add up representative volumes in the same way we add up representative rectangles. So when we add up representative volumes, especially of composite figures, we come up with the volume of that particular composite figure. Now, these are different examples of solids wherein we can determine the volume of using integral calculus. Now, this one, the center, the yellow one is the disk. Doesn't have any hole, doesn't have any hollow part. It's a solid. So as I've said, your 1 peso coin is an example of a disk. Now, a funnel is a different story already. So it has a hollow part, which is the center. So this could be solved either using the shell method. It depends on the user of the tool integral calculus, whether he or she is going to use the washer method or the shell method in determining the volume of this particular composite figure. I say composite because you have a different shape here, and you also have a different shape here at the bottom. Okay? In here, without these holes, these 5 holes, you also have what we call as the disk, minus the holes. You also have this disk. You have this, wait, huh? Okay, you can have, I'll use my pointer so you will see. Small, big class. So in here you have the solid disk without the holes, the big disk that is. You have here a smaller disk. This smaller disk, I think, is a portion of the cylinder that you see here attached to this disk. So the one here that is having this length along this axis is the cylinder. So this one is a composite figure because it has several shapes on it. Now this one is another composite figure, the bottle, somehow like a bottle that you have here. This part is a cylinder, while this part is a composite figure. We have here a piston, this part. So the volumes of this can be determined using any of the methods that we'll be discussing in a little while. Okay, so there will be three: the disc, the washer, or the shell method. Now, the shell and the washer method have hollow portions, whereas when you speak of the disc, all throughout your volume, there aren't any hollow portion, or there isn't any hole in your solid. Now, let's go to the disc. So, if we'll in terms of an example, a concrete example of a disc. So, if you cut your sweet potato, your kamote, these are discs. These are samples of discs that are being formed. These are, of course, samples of solids wherein we can use the disc method in determining the volume of. Okay. Now, if this is our disc, if this is the area rather, the one in blue that you see, and this is the chosen area that you are to rotate in this particular axis. You see this this illustration here that you are to rotate this particular area. You'll be forming just a single disc. So 1 peso coin, let's say for example, this will resemble 1 peso coin if you will rotate this differential area on this x-axis. Now, if you sum up these several differential areas rotated on this axis, you'll be forming somehow this particular figure here that you could see several discs. Okay, and then if you're going to take the integral or represent the volume of these several discs summed up in a form of an integral, in our previous example, in our previous lesson, by the way, class, we had it represented as dA because we want to determine the area. So area is equal to dA, where dA is either x dy or y dx. I hope everybody could still remember. In here, if you determine the volume, it would be dV. And since we talk about the disc, the area of the disc would be the area, the circular area of the face of the disc times its thickness. Okay, so that thickness of the disc, okay, annotate, just transfer this one here, you can see. So that thickness of the disc is this dx. This is the area, and this is the thickness of the disc, the ds. So the area times the thickness, it's dx because it's supposed to be integrated from A, starting here, to B. So starting with the lower limit of A, ending with an upper limit of B. So since you have several of this disc, it's just like you're summing up all the volumes of this disc. And that would give you the volume of this particularly shaped area, the blue area, rotated around the x-axis. So take note, the differential volume, because we want the volume, is equal to the product of the area of the face, which is pi r squared, taken from the area of a circle, times the thickness of the differential area, or shall we say, the thickness of the disc. So we have now dx. So it's like comparable to taking the limit of each of these. I'd like to represent this as delta v sub I, because you have several delta v's here. You take the summation of all these delta v sub I, starting from I equal to 1 to n, where n represents the number of this that you have. That would give you the volume of this entire solid. So dV is equal to pi fx squared dx. So this fx squared is the r squared, pi. Your r, the radius of this circular face of your disk, is actually the function itself, because this one is your function. So this point here is also your function of x, resembling the r. So pi r squared, or pi f of x squared dx. This is the one that you will be integrating to get rather the volume of this solid of revolution. Now, it could also be something like this in here, but take note, class, that the volume that we are just concerned in here is the blue one. So you are rotating your, this one, your area. The area is only until here. Now you're going to rotate it on this particular axis of revolution. You see this part here, which is hollow? This part here, which is hollow. Your solid is only in this part. In this particular method, you're not using the disk method already, but rather you'll be using what we call as the washer method, because your figure is rotated on a different axis. It's being rotated in here, here on the x-axis, not in here. Your limit of integration is still from A to B, but you have here your axis of rotation is already this x-axis above this blue line. You are rotating it in here, but this is where your area should be rotated on. So the result is something that is hollow. Okay. That's this g of x, as you can see here, is the hollow part of the solid of revolution. So this is just in contrast, or contrasting this method used in here on top and this one in here at the bottom. Okay, the solid that is being formed is not purely, shall I say, solid, because it has a hollow portion in the second illustration below. Okay, I'll go to the next slide if you don't have any questions. I'll just clear my margins first. Now, what about in here? Okay, you have dB is equal to pi. So you still have pi, but what happened in here? I'd like you to notice this one. You have the function of x. This is your function of x minus the k. This is the k. Your y equal to k line. This is here. Okay, that's your line equal to k line. In this horizontal line, all your y's are equal to k, whatever that k value is. So in determining the volume that is being formed, you are rotating this time, this particular differential area on this axis, the blue axis. Not here on the black axis, but in here on the blue axis. So what happened? The length, if this is your dA, your differential area, the length of this would be from here minus this one is this length. Okay, so length is equal to the function of x. The function of x class is measured from this x-axis going up to this point. So that is why you have function of x. This is function of x, the entirety of this length measured from the x-axis. If you subtract k, this one, minus k, you are getting actually this one. Only the length of your differential element. So this is the thing that you are determining. The f of x minus k is the L that you are determining, and in this case, it resembles your R. So this is just like comparable to having pi r squared dx. In this case, class, you're still forming a disk, but the axis of rotation is not on the x-axis, but on this line y equal to k. You see the arrow here? It's being rotated on this particular axis, which is y equal to k. Don't get, let's say, accustomed to or maanad na ikaw nga, basta axis of rotation, it's either just the x-axis or the y-axis. No. A lot of problems have axis of rotation that is not really coinciding with any of the axes of our Cartesian plane, just like this particular example. So since we are interested with the solid of revolution form, when this particular area is rotated around this axis, your R will be solved using this particular f of x minus k expression, which resembles, of course, the length of this differential area. Do you get it? Now, please ask question if it's not clear. Otherwise, if there are confusions, I will not be able to clear those for you. Okay? Now, let's go to the second one here below. So in here, it's the other way around. This is still your pi, this is still your r squared, and this is your dx. Why is this so? Remember, your y equal to k this time is still above the x-axis. Okay, this is your x-axis. And your y equal to k line is above the x-axis. You want to produce, I like to use the red ink, you want to determine the volume of the solid form when this particular blue shaded area is rotated around y equal to x-axis. So if you would be asked, so this should be your r, right? And this is your dx. If you want to find the dv, then pi r squared dx is the formula. Now the question is, what is this r? What is the length of this r? So that would be from this axis until here, that would be your k. From here to here, that would be k. What happened if you subtract this one? Isn't this representing the function of x? From here to here, measure all these points here are functions of x. So if these points, if the distances of these points from the x-axis is subtracted from the distance of this line, which is fixed from the x-axis, you'll be forming the radius or the length of this differential area. Okay, the differential area r dx. So this is now the reason why you have k minus f of x quantity squared, because this is your k. If you subtract, okay, why ko siya malapot sa dalo kasi na-confuse ka mo. Your k is from here to here. Okay, from x to here, that's y equal to k, so that must be k. If you subtract in particular this distance, you'll be getting the radius of this part. And this distance is function of x. So that is why you have k minus function of x squared, pi r squared dx. So changing the location of the axis, and especially if the axis of rotation is not any of your x-axis or y-axis in the Cartesian plane, changes the formula in determining the volume of a solid of revolution, as illustrated by this washer, and rather this method of determining the volume of the solid. Now, any questions so far? So this is determining the volume already for this. This is already determining the volume of this. In here, you'll be integrating from A to B. In here, the same thing. Why is it Miss A to B? Because anyway, your differential element has this thickness which is dx. And what is this boundary of dx? That's A to B. Same thing here, A to B. So these are the boundaries of your solid. Any question? Okay, so we haven't yet discussed a particular specific example. So let me clear my markings. Now, here we have horizontal axis of rotation. What about this one? Vertical. Now, in here, you will be rotating your axis, or you will be rotating your differential area on a vertical axis. So this time, the thickness of your differential area is dy. Your limit of integration would be starting from C to D, because these are the boundaries of this blue shaded area, the entirety of this blue shaded area. You will rotate this differential area. So I'm referring to this differential area now as x dy. That's your dA. So you are going to rotate it around the y-axis. So your differential area is x dy. Okay. Now, what is that x? What is this x here? That's the equation of this function, whatever is the equation of this function in terms of y. Why? Because it's horizontal already. So in terms of the volume, so you could see here the volume dV is equal to pi r squared. What's the r? In this case, that would be your x of y squared dy. So here, your limit will be from C to D. That would be for this part. Okay? Now, another scenario. What about this one? I'll just move this annotation. So we have this. Now, this time, your axis of rotation is not right on the y-axis. This is your y-axis. Okay, let me label it first properly so you would understand. Okay, that's your y-axis. This time, your axis of rotation is starting on the left side of the axis. Ari siya ho, x is equal to negative k. So notice that the equation now of the line is x, whereas kaina, ang aton equation is y, because our thickness is dx. Now, since our thickness is dy, so your axis now will be x equal to something, whatever is that constant, because now it's vertical. I'm referring to the axis. So how will you find the length of this r? So this r actually is this entire r, right? Your r will be the length of this entire differential area. This is your dy. Now, what is this length? All you know is that from here, from the y-axis to any point on this function of y or x of y, that is equal to the equation of the function itself in terms of y. What about this one? You need to account this because you need to add this small portion, this portion here, to this function of y. So that would be, you could see here, pi times the quantity x of y, this entire x of y, plus the k. Why plus the k? Because this one is to be added to this entire length of your differential element. Though this one is negative, isn't it negative because it's on the left side? You're going to make it positive. You're going to add, let's say for example, this is negative 1. You're not going to place here minus 1, but rather going to place here plus 1. Why? Because you're going to add 1 unit, 1 fixed constant unit to this whatever this is, the function of y or the x of y. Because now the entire sum represents the radius of this differential element that you will rotate not on the y-axis but on the line x is equal to negative k. So that's the reason why you have here pi, that's the quantity x of y plus k, those quantity squared, then multiplied to dy. Do you get it? You should understand the way you set up the radius of your differential area because it really matters a lot, especially in reference to the axis of rotation. Okay? Questions? And sige. Now we go to this one. In here, your vertical axis is on the left side of the y-axis. Now, what about if it's on the right side of the y-axis? So this is your y-axis and it's on the right side. So this is the time. So your r here will be just from this point up to here. That's your r, the radius of your differential area, which you need to multiply by pi. What is this r? Now, if from here to here is your f of y or your x of y, if you subtract this one, which is k, then that would give you the radius of this solid of revolution. We're going to rotate now this one here. Okay, so you have now x of y minus k, quantity squared, times pi dy is the differential volume of this particular solid. The matter, gid siya kung diin ibutang ang axis in terms of how you should write the radius of your solid of revolution. Any question? Okay, so last part. This is just like the same sa kaina. So last part is this one. So this is your y-axis. It's always the black line, which is our y-axis. And this is your axis of rotation. This is your solid. This is your area, which will produce rather your solid of revolution. So this is dy. And you'll have here the radius. Now, what is the radius? It should be from here to here. What's that? That's the k. The equation of this line. That's the k. Subtracting this one to this one, that would be your x of y. So the k minus the x of y, you square that represents already your r squared. This is your pi dy. So though they don't look similar at all, but they have the presence of the k in this particular three scenarios here. Because in these cases, your axis of rotation is not the y-axis itself. In here, it's the y-axis itself. So you don't have any constant added, subtracted from it, or a constant where your particular length of your function is subtracted from. Any question? In all four scenarios, the volume is computed as dV, which is pi r squared dy. So generally, it's pi r squared dy, integrated from C to D. It's C to D. They only change in the r expression. So this that's where they are all unique, but in terms of the form of the equation, they are the same. Do you follow? Do you have any question? Okay, so if there aren't any questions, I'll clear my markings and we'll proceed. So by the way, so we'll just contrast the two. This one is vertical axis of rotation. The function is in terms of y, meaning the variables that you will be seeing in your function are y variables. And your differential area, in this case, will be r dy. So it becomes a volume once you place here a pi and you square the r. But in terms of the area only, if I will label it here, in terms of the area only, that would be r dy, just like the way we have discussed it on plane areas. Okay, this is in the case of the vertical axis of our orientation. Now, in the previous example, just to contrast and review, we have horizontal. So our function is in terms of x, and our differential area is, what is our differential area if our function is in terms of x? So this is dx, and this is your r. So you have here your differential area is r dx. Differential area. If you want the volume, you place the pi and you square the r. That makes it volume already. So your axis here is horizontal. Here my markings, and we'll go back here and we'll have another one. Okay, so in this case, wala tani kay na I think ma-set up ang iya equation. So your dv in this case will be what? Can you supply the dv? dv is what? Pi. This is your, this entire thing is the r. You're going to rotate it on the blue line. So you have pi r squared dx. Your differential area is r dx. R and then this one dx. That's your differential area. Your differential volume is formed by squaring the r and multiplying it by pi. But what is this r? I think it was not written here. What is the r? Can you write on the chat box, please? Let me see if you know how to do it. What is the r expression in here? The r, remember, is this length plus this. That's the entire radius of your differential area. So what is your r squared? Okay, somebody wrote, it's f of x plus, okay, thank you, Carlos. So you have f of x. F of x is only from this point here to this point. That's f of x. But you need to add this one. So Carlos says f of x plus k. It should not be minus even though your k here is negative. So if the equation here is negative, you make the negative of that, or you make it positive. Because you are adding this length to this for the radius. Okay, I think this one was not, I did not place the equation. So for this one, we don't have any problem because our differential area, the dxr, is rotated right on the x-axis. It's just simply pi r squared dx. R dx is the differential area. Pi r squared dx is the differential volume. So these are your formulas on the different scenarios that may occur if your axis of your revolution or axis of your rotation is horizontal or vertical using the disk method. Okay, I'll clear my markings and proceed. Okay, so we have this example. Find the solid or the volume of the solid specifically by rotating about the x-axis. So the problem is specific. It wants the x-axis to be the axis of rotation. So this is it. By rotating around the x-axis, the region under the curve y equal to the square root of x Now, starting with the limits 0 to 1. So this blue area, you will rotate around the x-axis. Okay? Now, since it's to be bounded from x equal to 0 to 1, this 0 to 1 will represent your limits of integration. 0 to 1. Now, what is this differential area? So, I'll write here your differential area. Oh, sorry. It's super straight. Sorry, class. Straight down. So, this is your differential area. This is your dx, and this is your r. Now, your differential area will be r dx. Your x dx pi. But this one has to be squared. So, this has to be pi. Wait, class. Volume, it should be pi r squared. Okay, naka-square root na siya galit. Pi r squared, or I'll write it here because this is to abstract. So 0 to 1, you will have pi r squared dx. What is the r? The r alone is the equation of this curve. Y equal to the square root of x. That's your r. From here to here is your y as a function of x, which is square root of x. If you're going to square it, that's the reason why you have here pi x. This came from the integral of 0 to 1 pi square root of x, because that's your r, but it has been squared, dx. So that's the reason why you have here x. And the rest is just substitution of the limits of integration. So integrating gives you an x squared over 2, and substituting the limits give you pi over 2. Because this one, if you square that, that would still be 1. Have any questions? This is using the disk method. Revolve around a particular axis, the x-axis, which is horizontal. So your differential area in here is the radius times dx. Whatever the representation of that radius is, it depends on the equation of the function. But that particular equation of the function class should be in terms of x, because you're multiplying it with dx. Question? None? Okay, then I will proceed. Now, example 2. The first example is having a horizontal axis of rotation. This one is having a vertical axis of rotation. This time, it's the y-axis. Okay, you see this one. Find the volume of the solid obtained by rotating the region bounded by, so what is this region? It's bounded by this line, y equal to 8. Okay, you have that. Y equal to x cubed. This is the curve. Y equal to x cubed. And x equal to 0. So your x equal to 0 is your y-axis itself. This is your x equal to 0, the y-axis itself. So this area, the one shaded in blue, will be rotated around the y-axis. So the region is rotated around the y-axis or about the y-axis, and what will be formed is this solid. Amo na siya nga solid ang ma-form. So in this case, what's our differential area? The differential area is R. Whatever is this R? dy. Because your differential area is horizontal. As you can see here, it's delta y or dy. So if you place it here, you will have, actually this came from integral from 0 to 8 of pi r squared dy. Now you see now that you have pi, and what is this r? The radius is this equation of the curve in terms of y. So since your curve is written in terms of x, there's a need for you to rewrite it that way it will be in terms of y. So x equal to the cube root of y should be your g of y, or your function of y expression. So you could see here that it's now, I'll write here r is equal to the cube root of y, which is equal to y raised to 1/3. If you're going to square it, it's just like you're going to multiply the exponent of y raised to 1/3 by 2. So this would be now y raised to 2 over 3. The reason why you have here y raised to 2/3 as your r squared coming from this formula. So you have to use power rule in here. So y raised to 5 over 3 divided by 5 over 3, which is written here as 3 over 5 because it appears in the denominator of your variable y. So substituting the limit 8, because 0 will just make this one 0, the answer for the volume is 96 pi divided by 5 cubic units. Okay? We have questions? Okay, so I'm glad that it's very clear. Please ask questions if there are things that are not clear with you. Okay? So we'll proceed now. Now let's go to the washer method. Let's have a 5-minute break. Then we'll proceed with the washer method. Now we go to the washer method. So washer. So it has a hole. It has a hollow part. So it's not solid as the disc. Now, the cross section, we have this note. I'd like to read this ahead, that way I will not forget. The cross section that is chosen here is perpendicular to the axis of rotation. So what is perpendicular? So it has to be making 90-degree angle to the axis of rotation. Your differential area. So if you choose your differential area using the washer method, it has to be perpendicular. So this is an example. It has to be, let's say, dx, and this is your r. It has to be perpendicular to the axis of rotation. Okay, so for this particular washer, you could see in our previous in the first method, there's no hollow part in here. So that is why it's just pi r squared. Now in here, it's pi times the length of the outer radius. So the outer radius is this. This is r sub o. And the inner radius is this, until only that part. That's your r sub I. So the square of the outer radius minus the square of the inner radius multiplied to pi will give you the area. The area of this washer. Sorry. The area of this washer. If this washer is rotated around the horizontal axis, then this must be the x, because the axis of rotation is horizontal. If this area is multiplied by dx, I'll place here dx, this is now not area, but dv. Simple as that. So dv is pi, this is now squared, dx. That would be this differential volume of your washer. If you have several of this, on the designated limit of integration, then you will have the entire volume of the shape that you are accounting for. But what did you use? You used the washer method. You use the washer method because the area that you have determined has a hollow portion, or specifically the solid of revolution has a hollow portion. So you use the washer. So one thing, don't forget, that is why I mentioned it earlier on, that your axis of rotation should be perpendicular to the cross-section that is chosen, or the cross-section should be perpendicular to the axis of rotation. So take note, for example, this one. The area is this lavender or violet colored area, like a leaf. You see this leaf? Now, this leaf area, you will rotate around here, the x-axis. Of course, this part is hollow because in your entire area here, if it's to be rotated around this x-axis, sorry class, sorry, I did not have the annotated part. You will have this hollow portion. This one is hollow. So you cannot use this method. In the first place, if you're going to look at it, if you're going to visualize it, and if you allow me to use our vernacular language, galupad yata class ang inyo nga differential area. Why I say galupad? Wala siya nagatapik sa axis of rotation. Though it is perpendicular to the axis of rotation, but it's not connected to it whatsoever. Because if it's connected to it or attached to it, then you're not going to use the washer method. You're going to use the disc method. So whenever your axis of rotation is so chosen that it's perpendicular to the differential area or to the cross-section that needs to be rotated, and it's not attached to it, then you are to use the washer method. You get it? So this area, you're also going to rotate here. This area, you're also going to rotate here. Same thing with this area. All of these areas, you're going to rotate around the x-axis. So may hollow gid siya nga part, diri gamay lang, pero diri layo na ho, layo na gid ang iya hollow part. Layo na ang iya hollow part halin sa inyo nga axis of rotation. So in this case, you are to use the washer method. So how do you determine the volume? So the volume, if integrated, should have the limit, since this is, like to write here, this is dx, and this is your y. Your y is the difference of the outer radius minus the inner radius that are being squared. So you see, this is y1, this is y2. So y1 of x squared minus y2 of x squared multiplied to 5 will give you the differential area. Multiplying it with the thickness dx will give you the differential volume. So your limit here should be from A to B, because you're only going to get the volume starting with x equal to A to x equal to B. Do you get it? So pi outer radius squared minus inner radius squared dx. Dumduman nyo lang si Superman. Galupad siya. Why siya nag-a-attach sa axis of rotation? This one, if your axis of rotation is horizontal. The same area, leaf in shape, leaf-like in shape, but this time you will rotate it around the y-axis. It's going to be rotated on the y-axis, meaning this time, if this is your x-axis, and use this is your y-axis here, transfer mo, hindi mo na di siya pagtiyogon, dire mo na siya tiyogon. So, amo ni siyang wa. Sorry, klasa. Tama ka straight sa akon y-axis. Nagaslan siya video, kaya ang pag-draw gaslan pa. So, something like that. So, if you're not going to rotate it around the x-axis, you're going to rotate it around the y-axis, this particular area that we have, it still is perpendicular, though not attached, but it still is perpendicular to this chosen axis of rotation. right? O perpendicular, pero wala na siya gatagpik. So what is it? This is now dy. This is now your r. Or specifically, this is your x. What is that x? So that would be actually the square of the outer radius here, x sub 1. Just change to red. So this is your x sub 1. All of these are x sub 1, by the way. So you could see here, x sub 1 squared minus x sub 2 squared. So these are all x sub 2. So what are you forming? You are forming a washer. This is the area of the face of your washer. If you're going to multiply it with the thickness of the washer and integrate it from C to D, from this y value to this y value, you'll be getting the volume of the solid of revolution. So this is one washer that you are forming. You will have another washer here, another washer here. But in all of these areas, there are hollow portions in the middle. So it's not solid. So what you're going to use? The washer method. Any question? You can see here, for horizontal axis, it's ADX. For vertical axis, it's ADY. Just like with the disk method. Any question? Okay. If there are no more questions, then we will proceed. Okay, we go to example number 3. Find the volume of the solid form by revolving the region bounded by, so our region is bounded by y equal to square root of x and y equal to x squared over the interval 0 to 1 about the x-axis. Your axis of rotation is x-axis. What will you rotate on the x-axis? You will rotate on the x-axis the area bounded by these two curves, y equal to square root of x and y equal to x squared. Now, the limit of integration is 0 to 1. Now, in the first place, what is this area? Before you can set up this equation, you need to visualize a good visual of what is this area. That way you will know what method you will use. So let's see what is this area. Okay, so this is the area that we are to determine. This is the area bounded by the line y equal to square root of x and y equal to x squared. Okay, this one. Now, where do you think is the parabola here? Y equal to x squared. You're done already with sketching of the curve. Where your y equal to x squared is a parabola, right? If I'll change this one, this is actually y squared. It's not labeled, so I want to check if you know. So this one is actually y squared equal to x. This one is y equal to x squared. So tell me, what is this parabola? Describe that parabola to me. You're done already with curve sketching, so I'm just curious if you can still recall what is y equal to x squared as a parabola. Is it opening up? Is it opening down? Is it opening right? Opening left? Where is the vertex? HE? Y equal to, good. Somebody is writing here. Upward. Y is equal to x squared. Upward. This is Kyle Bico. What about the others? Do you agree with Kyle? Your y equal to x squared is a parabola that opens upward. You can write your answer on the chat box. Upwards, upwards. Sige, sige. So I'm happy that you recalled your sketching properly. So this must be y equal to x squared. Now, this one is a parabola that opens where? Parabola that opens to the right. Correct, Mr. Gimbal, to the right. So, to the right, then this is the one. Okay, so you have here y squared equal to x. So what is then the area that we're interested in? So the area that we're interested in is this area. This is the area that we're interested in. Leaf-like shape again. Now it's bounded. It says here bounded. Also, the area is bounded by on the interval, over the interval. So the area is to be integrated over the interval 0 to 1. So hasta lang de. Okay? Now, so that's the area. And you are to revolve it where? You are to revolve it in here. You are to revolve it around the x-axis. So just like what we have discussed a while ago, a few moments ago, if you use the washer method, what's the easiest differential element that you will use? Washer, wala man choice, kaya isa lain. So washer is what? You will have for the washer, what's your differential area? Vertical or horizontal in terms of the required condition that the cross-section should be perpendicular to the axis of rotation. So what then should be the orientation of your differential area? Vertical or horizontal? Oh. What happened? The differential area, how will I write it in this leaf-like area here, which you need to rotate around the x-axis? Will it be vertical or will it be horizontal? The differential area. How come? Vertical or horizontal? The requirement is the cross-section should be perpendicular to the axis of rotation. So how should I write the cross-section? The differential area cross-section. How should I write it? How should I draw it on this area here? Will I draw it like this? Or will I draw it like this? Vertical or horizontal? Vertical. Correct. Very good. Vertical, Mr. Quinto. So it should be vertical. So this should be your differential area. It should be vertical. Look, it's perpendicular to the axis of rotation. You get it? Now, this is your dx, and this is your r. So now, if you have that r, you could see how the formula for the volume is determined. So it's pi outer radius. What is the outer radius? This is the outer radius. So what is this outer radius? That would be square root of x squared. Because your equation here is y squared, you have to express it in terms of x. So you have now square root of x only because you need to get the square root of both sides. So square root of x squared, for this one, that is already x squared, and you need to square it. This came from So I'd like to use the red again. This came from this one, y equal to the square root of x. So this is for your y outer, and this one is for your y inner. So this is your y inner, which is x squared. You need to square it. So this 2 has to be squared. This is also squared. So that is why you have that. Outer radius minus inner radius. If you process this prior to integration, that would be x. If you square this, that would be x to the 4th. Then integrate, that would be x squared over 2. This will be x to the 5th over 5. Your limits are 0 to 1. So just substitute. So your answer is 3 over 10 cubic units. Did you get it? So notice your differential area or the cross section is perpendicular to the axis of rotation. Any question? Okay, so if there's none, we proceed. Number 4, rotate it around the x-axis. What is this? Rotate it around the x-axis. Okay. Sorry, class. Open. So this is the area bounded by the curve square root of x minus 1 and y equal to square root of x minus 1 specifically, and for this one, and the other one is y equal to the quantity x minus 1 squared. How come? What happened to this? Because okay, let me first do this one. Okay, wait, class, why can't it be shown as it is? Current slide. Okay, that's the volume. I'd like to show to you the class rate. Okay, this is the volume, and you should see the solid that it will be formed if this volume, rather this is not the volume, wrong term, the area. We have read already the equation of the functions in which the area that we are interested is to be rotated around the x-axis. So it should be rotated here. So we're still using the washer method. So you'll use a cross-section that is vertical because this cross-section will be perpendicular in orientation to this axis of rotation that is specified by the problem. So the thickness of this is dx and the length is y. Okay, so outer, so this is, let's say this is your y here. So square root of x minus 1 squared. Outer y squared minus inner y or lower y. Lower y is x minus 1 squared, and it is to be squared. So y sub I squared. And the limit that is to be used is here from 1 until here. So this is 1, 1.52. So you could see the limits of integration are 1 to 2, and you have here pi. So pi r squared, outer r squared minus inner r squared will give you the volume of the solid form when this yellow shaded area is rotated around the x-axis. Now, the rest is just mathematics. If you square this, that would be x minus 1. If we square quantity x minus 1 squared, would give you x minus 1 raised to 4. If you will integrate this part, that would give you x squared over 2 minus x. For this, limits will be from 1 to 2. If you'll integrate this, this would be, this could be integrated as a whole, or you can integrate it piece by piece. So this could be x minus 1 raised to 5 over 5. So you could see here u to the 5th over 5th. The u, the entire u that is chosen here is x minus 1. So you could see, since the du is just anyhow dx. So if you use power rule, that would simply be giving you u raised to 5 over 5, which translates to, what is the u? That would be x minus 1 raised to 5 over 5. Wherein you're going to substitute the limits 1 to 2. Why is this 0 to 1? Wait, class, 0 to 1. Why is the limit of integration here 1 to 2? And now it's 0 to 1. 0 to 1 here, you have u to the 4th. Why do you think was our limits of integration changed from 0 to 1 instead of 1 to 4? 1 to 2. The original limits is 1 to 2. Now, using the u, this one, the u raised to 5 over 5, the limits of integration that were used is 0 to 1. Why is that? Anybody? Would you know why it's 0 to 1? For the x minus 1 raised to 2 squared, why is it different? Why is its x limit 0 to 1? Not 1 to 2. 0 to 1, class, is from this portion until here. If you're going to substitute 0 to 1 here, this will be your answer. 3 pi over 10. Now, how come that it's just 0 to 1, not 0 to 1 is here? Whereas our area is bounded by 1 to, is bounded, or should be using the interval 1 to 2. Any reason behind? Why do you think the limits of integration were changed? In here, we don't have any problem because after this one, you just substituted the limits. So you have here 0 to 1 for your u. Why is that? Anybody? Why is it 0 to 1, not 1 to 2? I'm just curious if you know. If you do not know, actually, you can still solve it using expansion. You need to expand this one and then use the correct limits. Why do you think? Anybody by any chance would know why the limits of integration were changed? Has to be changed because we use the u as x minus 1 and du is dx. Why do you think, my dear students, was it changed? So I'll change this one to 0 to 1. I'll give plus points to those who can answer in the next quiz. Why is it 0 to 1? Wala, gid. Sige be. Plus bilang bago. I gave plus 5 on the next quiz for those who got it right. Let's see. The change in limits of integration during u substitution is substitute 2 and 1 to x in x minus 1 to get the new limits. Very good. Very good, Janessa. So I have already, you remind me of your plus points, Janessa. So that's the reason behind. Okay, I'll share to you the answer of Janessa. If it's dx, so very good. May ma-CHE ginide. If it's dx, your limit is from 1 to 2 because we're talking about dx boundary on the x-axis. Now, actually, if you just simply look at 0 to 1, you see here 0 to 1, and still refer to the same x-axis, you will not accept it because the 0 to 1 boundary is not even, the area is not even part of that boundary. But take note, class, that you already changed your x minus 1 to u. And your du will not be anymore the dx, the original dx, which is this thickness, to be evaluated from 1 to 2. So what you'll do, the original x limits that you have here, which is 1 and 2, you subtract 1 from that because you're not using anymore dx, but you're replacing it with du. So for this one, u is equal to x minus 1. So 1 minus 1. So that would be 0. 2 minus 1, so that would be 1. So that's the reason why your limits of integration changed here. So instead of using 1 to 2, you use 0 to 1 because you made use of this substitution equation. Okay? Now, if you find it complicated because it would have been easier, Miss Ali, it will not be one big of a headache for us. If it's just a simple case of power rule, good. So if you think that this would be a big headache for you and you'd rather make use of what you've learned in algebra and how this expression could be expanded, it's fine with me. If you don't use the u equal to x minus 1 substitution and du for the dx, then expand this and use power rule. Then you can stick with the original set of limits, which is 1 to 2. But if you intend to use this substitution equation, u equal to x minus 1, your limits has to change. Okay? That's a common, actually, class, that's a common overlooked mistake of students na kisa naga-substitution na sila pero ila-limit sa mumang gyapon. So that's one thing that you should consider when you do definite integration already. Once you use substitution, the limits of integration also changes depending on the substitution equation you use. Just like this. So we change our original limits in terms of x to the u limits since we're using already the u du substitution for x minus 1 and dx respectively. Okay, so the rest of these are just math. You just substitute. Okay, so your u raised to 5 over 5. So your u is 1 raised to 5 minus 0 raised to 5. So this is your answer for the volume of the solid of revolution. Do you get it? Very good, Janessa. You have any questions? Okay, so if there's none, before I close this one, I'd like to show to you the solid because why is it not going to show? Wait, class. Clear my markings. Hindi siya nag-show. So I'll just escape and show to you the volume. Class, ha? Ayaw ni siya, class, ang itsura niya. I don't know why if it's projected, you won't be able to see it. This is the solid that is formed when this area is rotated around the x-axis. So the volume of this solid is 3 pi over 10. Get it? Sige ha? Just ask questions if you have questions. So we'll now go to shells. Cylindrical shells. So we're done with disk. Now we go to volumes by cylindrical shell. What is common about plus the washer method and the cylindrical shell method is that your solid has a hollow part. So it's not really totally solid. as a hollow part. So either you use the washer method or the cylindrical shell method, depending on your comfort zone, kung which of these two methods you find easier to use. But if the washer method requires that your cross-section, or if the differential element has to be perpendicular to the axis of rotation, even if it's not attached to it, using the cylindrical shell methods also has a requirement. Okay, so let me just proceed. So take note of this. So I'll read it now before I forget about it. The cross-section this time is parallel to the axis of rotation. You get it? The cross-section is parallel to the axis of rotation. This one here. So if in the washer method, the cross-section is perpendicular, this one now is parallel. And take note, since it's parallel to the axis of rotation, it's not also attached to the axis of rotation. It is never attached to the axis of rotation because in the first place, it is parallel to it. So take a look at this one. So this is a cylinder comparable to a pipe or to a tube. So what about a pipe and a tube? So it has a central hollow part. So when you use the shell method, it's like you're using this method in determining the surface area of a cylinder. So you're done with your solid mensuration already in senior high. So determining the surface area, or shall we say the lateral area of your cylinder, is just like you cut through the side of your pipe or your cylinder, and then what do you form when you cut through the side? You form a rectangle. And what is the area of that rectangle? The side of that particular rectangle, I will annotate, the side of that particular rectangle is 2 pi r. If I'll cut here and I'll open, I'll be forming a rectangle, right? Imagine I'll cut here, so I'll be forming a rectangle. The circumference of this original pipe or tube is this 2 pi r, or simply pi d, pi times the diameter, and that would be now the length of your rectangle. The width of your rectangle is the height. This is the height. This is the circumference. This entire thing is the circumference. So now you have 2 pi h representing the height of your cylinder or your tube, and this x as the, what is the x of this rectangle? It's the distance from here to here. That's x. That's x. So 2 pi x times this one allows you to determine the area, the lateral area of this particular tube. Lateral area. So we are determining the lateral area. What about the volume? So it's like the area, this area that we're talking about, we integrate it on the differential of x, or the thickness. This is the dx here. So just like this one, and then having this particular height of your rectangle, this is the length of your rectangle, the pi d or the 2 pi r will give you the area. It's just the area because it's just the face. I hope you can imagine. It's just the face. You have this as the height, and this circumference here, based on this radius measured from the y-axis, is just the length of your rectangle. Length. And this is the height or the width of your rectangle. So it's just area. But if it is integrated using this dx from here to here, then you determine the volume of this shell. You could see this one, how many shells you have. This is one shell, another shell, another shell. You'll be determining the volume of the solid form if this area is rotated around the y-axis. So the reason why you have this is being cut for you to see the different shells. So this is one shell, this is another shell, another shell, and another shell. If you sum up all the shells, then you'll have the volume of the entire solid form when this area, this is actually the area, this area is rotated around this axis. One thing that you should never forget when we talk about using the shell method is that the cross-section chosen should be parallel to the axis of rotation. This one is parallel to the axis of rotation. So the distance, the very important thing again that you should remember is the distance of this differential cross-section or differential area from the axis of rotation is actually the thing that is determined by the equation of your curve. So you see this? That's the x. From here to here. From here to here, that's the x. Whatever that x is of your function. In this case, it's y of x. The height is from here to here. Then you have dx. Now, in terms of the limit, since you have dx, it should be from a to b. Now, dv is a dx, so you have 2 pi x. What about this h here? That should be your y of x. This is your y of x. This, let me just use a different color so you will, that's the appropriate here. Let's see. Sige. Get para makita higit siya. Amo ni siya ang curve class, oh, para clear. Amo ni siya ang curve na y, sorry. Okay, na y equal to x. This y equal to x changes. This is different. This is different, y equal to x. This is different. This is different. So, lain-lain ni, or different, nga lain-lain nga law ay different y of x for any point here on your equation y of x. What is important is it should be expressed in terms of x. Okay, let me just go back to the original thickness. So you could see here that you have 2 pi x, it's fixed already. 2 pi x, the distance of this cross-section or differential area from the axis of rotation. And your y of x is changing. This is changing depending on the area that we're talking about. It could be this small area, so your y is different. It could be this tallest cross-section or differential area, and your y will be different here because it depends on the equation of the curve. So now you have here y of x, and you have dx. So since 2 pi is a constant, you place 2 pi before your integral, so you have x, y of x, dx. Remember, since we're integrating in terms of x, your function should be expressed in terms of the x variable. Okay, it should be expressed in terms of the x variable. Any questions so far in here sa babaw before I go sa dalawang mga illustration? So you are summing up the volumes of all the shells of your solid of revolution to get the volume of the entire solid. Now, what about this particular solid of revolution here? It's leaf light. A while ago, we used the washer method for this because our axis of rotation class, a while ago, if you could still remember, our reading atom axis of rotation. So it's washer because your cross-section, this cross-section is not attached to the axis, but it's perpendicular to it. Now, in this case, your axis of rotation is the y-axis. So this is your axis of rotation. This has to be your axis of rotation. You cannot use this axis of rotation if you're using this formula, because based on our requirement, the cross-section is parallel to the axis of rotation. So this is the cross-section that we're talking about. So if this is the axis, this is the cross-section, this is the differential area, the axis of rotation has to be parallel to it, not perpendicular to it. In our previous example, under the washer method, amo ni siya ya. Rusubong, dapat amo ni ang inyo axis of rotation. Okay? Now, for this particular axis of rotation, the same, actually, it's already written here. The distance of this particular cross-section or differential element from the axis of rotation is fixed as x. Anywhere in your differential area, it's x. But this one is different than this. Than this. Than this. Lain-lain ni sila yung kataason nyo. Kag lain-lain values ini nila. So how do you get it? So it's still 2 pi x. This is fixed as 2 pi x. But this one class, the, shall I say, the width of the rectangle, comparable to this h here of the pipe, the width of the rectangle is actually the difference of from here to here is y1. From here to here is y2. So if you take the difference of y1 and y2, that would be the length. That would be the width of this rectangle. So that is why you have here y sub 1 of x minus y sub 2 of x. Then you just need to subtract these two, whatever is their representation. Important lang nga dapat ini in terms of x. This one should also be in terms of x. Do you get it? So 2 pi again is written before the integral. You have x placed in here. It's fixed and you have this 2. So for the y1 of x, whatever is its equation, as long as it's in terms of x, subtract from it the y sub 2 of x. Okay? Any question? It's like this class. Amo na siyang gwa. This is one shell you have, another shell for this area. So the area, that area is this actually, the leaf-like area. That's it. So these are the different shells you'll be forming if the cross sections that you have will be rotated on the y-axis. Any question? Okay, so let me clear my markings. Proceed. Okay, so let's go now to a specific example. You have that area. Find the volume of the solid of revolution formed by rotating the region bounded by the x-axis. So this is your, let me just change my form. This is your x-axis. The graph of y equal to square root of x. So this is actually y squared equal to x. So it opens to the right. So this is your curve y squared equal to x, equivalent to that equation, bounded by the interval 0 to 1. It's going to be rotated on the y-axis. So it's here. This is where you're going to rotate it. So if that is the case, this is your axis of rotation, and we are talking about the shell, so we might as well use the shell method. Your cross-section or your differential element has to be this. Okay, so you have here dx, and this is your h. That's your h, which is the width of your rectangle. So your volume is equal to 2 pi. Distance of this cross section from here is x, and the height from here to here in terms of x is square root of x dx. The limit is from 0 to 1. So you can see now that 2 pi was written before the integral. You need to combine these two using rules of exponents. So that would be x raised to 3 halves. Power rule will yield x raised to 5 halves. Okay, over 5 halves, so that would be 2/5. So your volume is 4 pi over 5. Questions? Okay, so no questions. Okay, I think I have one more here, class, and that's it for this topic. And this is the solid that will be formed. The solid that will be formed if this is your cross section, rotated here. Several cylindrical shells. So one shell here, another shell here, another shell, and this will have it. If you sum it up from 0 to 1, this will be the solid. Okay? Let me check. I still have another one here. It's 7. So find the volume of the solid of revolution formed by rotating the finite region bounded by the graphs. So these are your graphs about the y-axis. So this time, you will rotate it on the y-axis. In the previous example chosen, it's rotated here on the x-axis. So this time, it's on the y-axis. So your cross-section should be parallel to, chosen such that it should be parallel to this axis here, not perpendicular. In our previous example, this is our axis. Then not now, because this time we're using the shell method, so we're using this axis. Okay, so same thing. So you will have, let me just change. Volume is equal to integral. So this would be dx, and this would be the width or the height of our rectangle. Now we will have the limits then. Dx is from 1 to 2. 1 to 2. Okay? And then you will have 2 pi. Your r is from here to here. So that would be x. And this height would be the difference of these two. You will have the square root of x minus 1 minus this one. Quantity x minus 1 squared. Change this. You have dx. So that's the thing that you see here. The 2 pi was written before the integral. You have x and the square root of x minus 1 in here. And this x also distributed to these two expressions here. So you have this one in here. And you will have, if you will use the substitution equation again, so you will have u equal to x minus 1. So in this case, your x is equal to u plus 1. Your du is equal to dx. Okay, so you have now u plus 1 for the x, and this one, your x minus 1 is square root of u, as you can see here. Then you have dx, and you have 2 pi. This should be already du because your dx is du. It should be now, it's not able to change it, du. Then for this, you will have u squared for x minus 1 quantity squared. So u squared, and this one is x. U plus 1 for the x. You have this. So your limits will be changing because we have now changed our variable. So we changed the 1 and 2 to 0 and 1 because your u is x minus 1. So 1 minus 1, 0. 2 minus 1, 1. Okay, so you have this. And after that, you will just need to distribute the square root of u here and use power rule. In here, you will just distribute this one also in here and use power rule. So the volume of our solid is 29 pi over 30. Do you get it? Any questions? No more questions? Sige. So we'll continue, ha? Let's see. I'm not sure if I have another illustration. Now, this is the solid one. If it's rotated here, if this is your axis of rotation, and this is your cross-section. So this is the solid that you will be forming. Hi? Now let's see. That's the substitution equation that I placed there. Now, this time to practice. For example, number 7. Find the volume of solid obtained by rotating the region bounded by y equal to x minus x squared, y equal to 0. This is actually your x-axis, and you are to rotate it about the line x equal to 2. So not on any axis, but on a different line. What about this, Miss Ali? So let's see. Okay. So your region is bounded by this curve, by the x-axis, because it's the y equal to 0 line, and it has to be rotated on the line x equal to 2. So the line x is equal to 2 is this one. Okay, this is your area, and it has to be rotated on the line x equal to 2. So what would be the best way to solve this problem? Here is your line x equal to 2. It is to be rotated here. Let me just put this up. Okay. Hang in there, class. We're about to finish. So this is your axis of rotation. This is the area that you will have it here. And since we have chosen the vertical cross-section or the vertical differential area, you're going to use the shell method. The shell method. Okay? So ano gani ang shell? So let me just say. The volume is equal to 2 pi x h dx. That's the dv, right? No problem with this because this one will have a distance of from here to this particular, let's say I'll draw the cross-section here. Okay, I want this distance, class. I hope you're not bored and I hope you're not yet so spent. What is this distance? From this line to this cross-section, what is that distance? If I'm going to ask you. What is the distance of this chosen cross-section from this line x equal to 2? That would be what? That will be our distance x. In this case, it's not a fixed x, but it's an equation or an expression because our axis of rotation is in here. What should it be? Halin ini siya amo ni ato gusto mabalaan. Ang distansya halin sa aton axis of rotation and the cross section. What is this distance? That's x equal to 2. What is this distance from here to here? That would be x. So what is this? Ay, very good, Mr. Gimbal and Ms. Boquinto. Okay, very good. So you have 2 minus x. So hindi na tamaanad nga permi lang x kay kaina, permi lang siya x kay tungod ng inyong axis of rotation, ara man lang sa y-axis mo. So x ang siya permi, isubong hindi na siya dao. So this is where principle really is being applied. So anong distansya sang sini nga cross-section halin diri. So ano na siya? This is 2 minus x. Anyway, written here. Okay? So if you're going to write, that's it. So 2 pi, 2 minus x, this is our usual x class. Amo ni siyang usual x ta niyo. Horizontal distance of our cross-section from the axis of rotation. What about the h? This one. That would be x minus x squared. This one. The h. The y in terms of x. So that's x minus x squared. That's it. Let me just close this. Okay, I cannot do it. So you have that one. We just do expansion here. 2 pi is set aside. We just use the limit 0 to 1. Now, another thing class, wala ginhatag ang limits of integration, no? So wala ginhatag. There was no mention here about the limits of integration. Simply find the volume of the solid obtained by rotating the region bounded by this curve, this line, and rotating it around the line x equal to 2. How would you find the 0 and 1? The 0 is easy because you could see that your curve already crosses the x-axis here. So it's 0. What about this? You just simply get the intersection, the point of intersection of your curve and this line y equal to 0. So you just set this to 0. 0 is equal to x minus x squared. We have discussed this under the topic of plane areas. How to get the point or points of intersection of curves or curve and line. Okay, so you have that. You'll have x minus 1. So you see, if you equate these two factors of the original equation to 0, you will get the 0, x, and the x equal to 1. That will give you the limits of your integration. Do you follow? So that is why you have 0 to 1 here. It's not given in this problem. So that is why I included it in here because there's a lot of things that you need to think and apply the principles that you've learned based on the examples we have discussed. Okay? Now, let's proceed. So I think you will have the answer here, which is pi over 2. So this is the solid. Okay? This is the solid form. And the answer is pi over 2. You have one for this area. You have another one for this. You have another one for this. It would be like your shells. You have several shells to sum up. Okay, time to practice again. Let me just clear the markings. Find the volume of solid obtained by rotating about the y-axis, the region between y equal to x and y equal to x squared. What are these regions? Okay, let me push this first. Find the volume of the solid obtained by rotating it about the, let me just underline this, the y-axis, and the region is bounded by this line and this curve. No points of intersection, so you'll be the one to determine the points of intersection. So this is your line y equal to x. Okay, y equal to x, and this is your curve y equal to x squared. A curve that opens upward. So you have another one here, and you have another line here. Y equal to x. By the way, your y equal to x line, if x is positive, your y is positive. But if x is negative, your y is negative. So, ang isa kari na di siya yung plus sa dalo. Ang ini nga line, ari diya sa dalo mo iya nga continuation. Or let me just use the blue ink. Please bear with me. Okay, we're almost done. We have this. This is your line. This is your entire line. Y equal to x. This is your curve. So the solid that we're going to form is this solid here. This differential area or this cross section. I'd like to use a different color so you will see. This cross section cannot be seen. It's yellow. This cross section. Now, that cross section is rotated around the y-axis. So it's another shell method. This cross section is rotated around the y-axis. So this one is easy because in terms of the distance of this cross section from the y-axis, it's just simply x. However, in terms of the height or in terms of the width of the rectangle, it would be the difference of this y equal to x and this one, x minus x squared. This one. Sorry, x squared. This is x minus x squared. So that would be the height of this already. Now to check on the solution, you just set up again the volume equation. So 2 pi x from here to here is still x. And as to the height of the shell, that would be x minus x squared. And you just substitute the rather do expansion, x squared minus x cubed, and 2 pi will be placed in here. Okay? And the rest would be just your mathematics. Sorry. You have any questions, class? So whenever you're solving for volumes, you always attach cubic units at the end. If it's area, square units. Though the units are not specified, but it's important that you affix the degree of the units because it's also reflecting your understanding of the degree of your units. Now, do you have any questions?